to ECGR 4101, 5101. This is lecture number 4. By popular demand, I've had several people mention to me that they had not, they had a little bit of weak background in C. Just as a show of hands, how many of you think you're pretty good at C? How many of you would like to have a lecture or two on C fundamentals just to brush up? All right? That's what I figured. So, today I taught for another faculty member, I taught the C refresher course, and I had a lot of people there who said, so we're going to go over a little bit of C. These notes I sent to you via PDF, so if you just want to take minor notes as we go along, and you could print these out later. So, the whole idea of C is that it's a nice high-level language where you can give symbolic names for variables, very similar to how you use mathematical equations in algebra and other disciplines along the line of math. And you can give them not just a single letter, A equals B times C, but you can actually do a whole bunch of more descriptive names and letters associated with your variables. And I do recommend that. So, we're going to look at a little bit of abstraction of the underlying hardware. So I'm going to go into the C first, and then our next set of lectures will be based on Chapter 3. So make sure, I did tell you last week to read Chapter 3, right? So now you really, really need to read Chapter 3. I'll put a homework assignment out there that will rely on you knowing. Actually, I'll put some homework out there that will practice C programming language. So at least you can get some practice with this, and then the homework after that will be on Chapter 3. So, the nice thing is, you can provide abstraction of what the underlying hardware is without really having to know, is it 16-bit wide, is it 32-bit wide, do you have a separate floating point multiplier piece of hardware equipment. So the nice thing about C, actually, is it's very portable. You can move it from one board to the other. So, for example, we moved a lot of code from our old Renaissance board that had a 16-bit processor. That means it moved data that was only 16-bit wide. And we moved it to this board, which is 32 bits wide. So the nice aspect of the C code is it was able to be moved with only minor changes needed. It is very symbolic, meaning, and to that respect, it's also very logical. So if you want to add, very much as in adding two things together in equations, in math, you just do the same thing as it shows up there for multiply B times C. And it also safeguards against bugs to some degree. Now, one example I gave in my in a class I taught earlier today, and that is, here's hoping I can even get it somewhere. Let's say you say float A, and let's say you say integer B and C. So if you say B is equal to A times C, is that allowed in C? Yeah, it's allowed in C. Does it make sense? Well, yeah, it kind of makes sense. There are two numbers that you're multiplying together, two variables you're multiplying together, but the thing is, C allows you to do that with a floating point number and for an integer. And in some cases, it doesn't really make sense. In fact, in some cases, when you're doing things like divide, you really need to take care of what's going on, because if you have a division operation, of course, keep in mind, C is an integer, and A is a floating point. Integer means you don't have anything beyond the decimal point. So how precise are you going to be? It also gets a little bit more dicey in the fact of, is this operation done in floating point or an integer? It all depends on the compiler. In some compilers, it will immediately convert this C into a float. It'll do a, which is a float, divided by a float. It'll get you a certain value, convert it over here to an integer. So it'll chop off everything at the end. So what it comes down to is that, you may introduce bugs based on changing the representation of your numbers. We'll look at that a little bit later. So, you're going to be working with C projects, or C++ projects. And a project, as you've been playing with the IDE, and as we found out from Mr. McLean a couple of days ago, actually, that was a week ago, wasn't it? That a project is something that you create, that you're going to take a whole bunch of pieces of code, put it all together, compile it, make something that runs, and use that code that runs. And so in this case, you're going to have, as an example, you could have Lab 7 as a project, and it will have a couple of C files, maybe a couple of C programming language include files, maybe an assembly language file, and maybe an assembly language include file. This is Lab 7 all the way down at the end. So it's going to have a lot of different modules. And in fact, right now, when you do a compilation, it already has a couple of files available for you to look at. Plus, there are some include files that you may not even reference. We're going to go over that in later set of notes much later, but you're going to be using this integrated development environment to do everything, to write and edit your code, to save your code, to do your compilations, to do, we're going to look at later, linking, loading, executing, debugging, all the little toys and bells and whistles. By the way, if you want to read ahead, you can go to chapter number 4 in the book, and it actually has a lot more detail on how to use the integrated development environment. It actually has some step-by-step processes for you to use, and explains a lot of stuff in there. But I'm going to be going over that in more detail in a later lecture. The whole idea of lab number 1 is to get you to touch the board. By the way, how many of you have actually finished it now? So you two said you'd done it. Somebody else said they had finished it. Okay. We have till Monday. And how many of you, just raise one hand for each lab pair, how many of you do not have your own board that you have to check one out from us, from Eddie Hill? Raise your hand high so I can count.
Not yet.
And remember, 1 per lab pair. So 1 hand per lab pair. Hold it up high so I can count. All right, 1, 2, 3, 4, 5. All right, so the rest of you bought a board. So somebody showed me their board today. Was that you today?
Yeah.
I can't remember who showed. Yeah, you showed me. You just came in today, and it was $100 plus $8 shipping, and you got it from Future Electronics, and it came in how many days?
It was like
2 days?
2 or 3.
Yeah, because they have someplace nearby that you can get it from. And then you get to use that for your senior design project. Yeah, we'll see. All right. So again, in this entire code package that you call a project, you're going to be working with a whole bunch of different files, probably modifying one, compiling, testing, modifying it again, compiling, testing, and then maybe going off to another one, compiling, testing. So there's a process that you're going to follow. So let's take a look at that process. Compiling a C program means that you take your source and your header files. By the way, that's C source, header, and also assembly language and assembly language include files. And you'll run it through a preprocessor that will add in macros. Remember the pound define that we talked about earlier? It'll take all those pound defines, it'll put it into your, it'll make the replacement inside your code. It will also start to look at parsing your code, so that if you have something in here like B is equal to A times C, it says, that's good, I like that. But if you have something like B equals 2 times AC, it'll look at that and say, I don't understand this. because here are two individual different variables and there's no operator between them, and so it comes back with a syntax error. The compiler then will take this source code that you have and will create machine language instructions that the microcontroller or microprocessor will be able to work with. Now, in the process of that, it's going to create what's called a symbol table. So as you can imagine, if I have defined A as a float and B and C as an integer, it would be nice if we kind of kept track of those. In other words, to say that, yeah, somewhere we're going to find out that A is going to be allocated 4 bytes and it will be a float. B is going to be allocated 4 bytes and that's going to be an integer. And C is going to be allocated 4 bytes and it's going to be an integer. And that table will be set aside for you to look at later, because think about this. Each one of these is space inside RAM. It's a temporary store place for all the calculations. The machine, the computer, the compiler needs to know how big that space is to allocate, because the first one is going to show up at some memory address in RAM. In fact, I've got an example of that later. In fact, here I'll just go forward a couple of slides. So in this case, it says that our RAM starts at memory address 00000000. So our RAM is all the way at the top. RAM is that space that is a temporary scratch pad for you to play with, where you put temporary variables. And in the world of a microcontroller, it's an area where you do not put programs to execute. It's reserved only for data, and it is not for putting your program instructions. That's actually put in ROM, read-only memory, flash. And then all the way at the end, we have what's called a linker. A linker is that device or that part of the compiler that will actually take your machine instruction code, and it will take some existing library files, like those files that hold the definition and the code for what printf does, for example. Or maybe something like, I'm trying to think of another good library, string copy is another one that you might have seen. So it's where all of those extra wonderful, already written functions that you could use, and it's stored off. Now keep in mind that if you don't use them, the compiler typically is smart enough that when it goes through and links, it doesn't bring in that code that's not used at all. And that's really good for embedded systems, because you want embedded systems programs to be small. And then you generate an executable image. That executable image actually will have the address of where it's going to start to execute. Specifically in memory, if we look at our space right over here, it says, oh yeah, on-chip ROM, it says program ROM, write only. What does that mean? Program ROM, write only. Why isn't it read only? Well, one way that they run this and protect some stuff is that you actually, when you write into your program, into the chip, you write it at this address, and when you read it from another address, but it's the same space. It's just the way they handle the addressing inside the chip itself. But when you do your compiling, it'll say, all right, I'm going to start to put my program starting here, memory address 00F80000, and I'm going to start to put stuff in there. Whatever your program is. So in the compiler, remember, we're parsing the program to identify the pieces. Things like equations will be checked Variables will be validated that it is what you say it is, that you're using an integer like an integer. And by the way, very often if you it will allow you to use a float integer together. Again, you can force it or cast it, as we say, to look like something else if you do something like this. In this case, you're going to say take A, create a integer out of it, then multiply it with C, and then go ahead and go. Now, can you think of a situation where that would result in a different operation than if you said, in fact, I'm going to have you turn to your neighbor and do this. Then if you said, can you see this? So you're saying, you know what, I'm going to put it up on the screen. Dock camera. Because some of you probably can't see that. Oops.
Still can't see that.
You're so picky. Gosh. So we said float A, int B, int C. So if we have some code here, can you think of a situation where B equals to int A times C will be different than already. So give me, talk with your neighbor for a second and give me an example of what you think, just one example of how that would be different. Something, some value in here that would be different.
What is that supposed to be?
That's an A.
This is an A right here.
How does it convert to an integer? Is it just truncate everything, or is it 5.5?
By the way, when you cast it, if it's a float and you cast it into an integer, it truncates. It doesn't round.
Okay. Whenever A is... This is an integer. Inverse and float. That's the whole thing. This one times the float.
All right, how many of you have no clue what the heck I'm asking? Be honest. Okay, so give me a good. You have no clue, or you have an example?
I have an example.
Okay, good.
Yeah, we can choose A as 2.5 and CS2. Okay. So for in the first case, when b is equal to integer of a, it is
For B is 4 now.
yeah. In the other case, it will be 5.
Okay? That's as an example. Of course,
Move it up.
and this is an example of, oh, does this make a big difference? Hell yeah, it does, right? You have a distinctly different number there that's being calculated between the two. And again, in the case of both of these, I am specifically forcing and casting the same operation, or casting these two to be the same data type before I do my calculation. So in this case, I'm forcing, this is a float, I'm forcing that to be a float. In this case, this is an int, and I'm forcing this to be an int. And in the end, of course, it's going to create an int out of it. And in the end, if you didn't force that, there's no idea what the compiler would give you. Well, there is an idea. You just test it and see what happens. Because often what they do is, it all depends on the compiler and who makes it, of what it will look like. Right? By the way, apologies to those of you who have seen this lecture now twice today. Does it kind of solidify everything? Good. Maybe that's a good reason for you guys to go back and view the old presentations, right? That's why I put them out there so you can look at it. By the way, I've had a spam, probably a spam email, telling me that my videos out there are excellent and they're better than most of the crap out there, and that I should pay them money to make them more popular so more people visit them. So I just want to touch on this again. We're going to go into a lot more detail on this in Chapter 3, but I want to point out what is our address space. Our address space goes from 0000, 0000. How many bits wide is that?
30.
Bits? Bits, 32, right? All the way down to F. How much space is that?
4 GB.
All right, 4 gig. Looking at this, how much space do you really have for RAM? How much RAM space do you have? How much RAM? Oh man, this thing's not working. Come on. Oh, that's not good. This doesn't work anymore. I broke it. So, how much RAM space? How much RAM? So I said RAM goes from 00000000 to 0001 F, which means we have hex 2000. I did that right. 1. I still didn't do that right. How about this? Does that look better? Oh yeah, what do you know? Oh good, so I could fake that I knew what I was doing. 0000000001 which means we have hex 1800 bits, bytes, words. How many? How much? Bytes. And again, that's hex. So how are we going to define that? Who's got a quick calculator here, right? Here's my favorite. View scientific. We'll go to hex. We'll do 18000. We'll change the decimal. So it is 98,304 bytes. That's a kind of screwy number, isn't it? But that's what it is. So, we're going to look at variables when you're working and running. So there are a couple of types of different variables. And this looks a lot better. I don't know why this thing is coming off the screen, so I'll have to have them look at this too. Again, you have variable data and you have fixed data. Variable data means there are variables that you will use inside your subroutines. These are called automatic because they're only used inside a subroutine and they don't have their own special space allocated in RAM. So if you were to look at this, it may actually show up in this RAM space in here. It may show up in this RAM space right here. Oh, there we go. Oops. This is gonna go bad. I could tell.
No pen.
I have never seen this before. They're not allowing me to use the pen in this. All right, well, I'm going to go on. So in this space here is something called a stack. Does everybody remember their stack? The stack from ECGR 3183. Yes? Yes? My compies, yes? How about my graduate students? All right, so you remember the stack is some area in here that you're going to use for temporary storage when you jump to a subroutine so you can return back from that subroutine. This is where all that stuff is stored. So those are called automatic variables or temporary variables. Then you have static variables that have initial values or no initial values that are more or less global and they're able to be used by many subroutines. Then you have constants that never change. And so the compiler is smart enough to put that in ROM because they never change. They're just going to pull that information later. Strings is a good example. Maybe you have a string that shows up on your screen. So you should save that in your program area or in the flash area so that since it never changes, you just pull it from there and byte by byte pull whatever might be stored. And of course, programs are stored in the ROM area or the flash area. By the way, I'm going to use flash and ROM concurrently. So here's a good example of local versus global. So we have this subroutine here, or function, called chapter 12. Are you passing anything into the function? No, you're passing nothing in. Are you passing anything out? All right, and then looking at this carefully, does this function have any useful function at all? It doesn't really appear to do anything worthwhile, but we'll just assume that it does. So, somebody got a trip to the... No, you didn't get a trip to the prize closet. You'll have to do the... Have you had a trip yet? Okay.
Did.
Maybe next time. Yeah, you got a trip to the prize closet. Yeah. She got stress ball. I notice you're not using the stress ball, so this must be a nice, easy... Oh, now she's using it a lot more. Nice, easy lecture. Going on... So we have 3 local variables, or 3 temporary variables, that once we execute this subroutine, chapter 12, they will not be useful anymore. They will not do anything. And here's a global variable that will be used by a lot of different programs. So, does this function here, all right, those of you who have already been through this today, keep your mouth shut, right? So, oops. So does this function here do anything to change the global variable? So will the global variable change at all by running this function? I'll say grad students. I'm going to pick on somebody. Young lady all the way in the back. Yes or no? Does it change anything?
No.
Okay? She says no. Do you agree?
No.
You agree with her or you say no?
No. It won't do.
And nothing will change. Okay? Everybody agree with that?
Inside this function only, it is.
Alright? I want to point this out. Right here. Here's a global variable. You say 3 is equal to the global variable. It's hidden all over in here, but this function will actually change in global to be equal to 3. And so when it ends, when this function ends, that global variable will equal to 3. So yes, this function does do something to a global variable. It just sets it to 3. Does that sound useful? Not really. And oh, by the way, this last line down here could be simpler.
Just 0. Okay.
Actually, this line could be really, really, really simple. Pardon me? All right. So this line right here could be out local b is equal to 2 times in local. By the way, what is the value of out local b after it executes that line?
6.
So out local b is going to be equal to 6, you're saying?
Yeah.
10. Yes.
6, 10?
6.
6.
Do I have anything else? Okay. In local, when it executes this line, the value of in local will then be 6. Right? In local minus in local plus in global. So in global is going to be 3 times 2 is 6.
It's minus.
Minus, which means that this is going to be in global plus in global. This is one of the traps I want to point out about writing software, is what a convoluted line. And in fact, if you look at everything that's going on in this line, or in this code, it can pretty much be represented by, first of all, one line of code, that being this right here. And it probably is really a part of something else. But notice that you're setting this equal to something, you're doing it, you're never using it. Be really careful about what variables are being used and how you're setting them. Because very often, many things could just be a single constant. Here's another example, so let's take a look at this. Is there a global variable? And it is equal to 6. So as we're going along here, if we're executing main, and we are executing this line, by the way, this is too long. This should also be a comment over here, so I'll have to fix that when I think about it. So we're setting A is equal to 10, B is equal to 16. We're going to call this subroutine, and we're passing A and B into this subroutine. So when we first execute the subroutine, squared is going to be taking this value, passing it into here, and then it's going to be multiplying. Wow, that's a lot of work, right? So the first time through, what happens? Well, A will be passed into compute, which will be mapped to X and Y. X and Y are local now to this subroutine, so that when we execute, by the way, I use subroutine and function interchangeably, because in the old days, when I learned Pascal, it was called a subroutine, so sorry. So in this case, X is going to be passed into squared. X was 10, passed into here. 10 is going to be passed into here. 10 by 10, 10 times 10 is equal to 100. We're going to return the value of 100. So Z will be equal to 100. Then Z is going to be equal to squared. What is Y? Well, Y was what B was passed. 16 is passed into here. 16 by 16 is 256. So we go back up to here. 100 plus 256 plus 6. 362 will be returned up here. So C is equal to 362. Of course, then it just ends. So hopefully there was something that happened to C right after that. So I just wanted to point out that the situation. By the way, what is it called when you actually say this about the function compute and squared? It's called what? Prototyping a function. And you need to make sure that that is done when you start up. All right, let's look at some control structures. You have better know all this if you've done anything, right? C is just simply if else. There's a condition inside. I've already done one of these in class. If the condition, then do this action, else do this action. Keep in mind that this action could have curly brackets with all sorts of lines inside. All right? The switch, have we talked about this in this class? I guess not. Is simply, you put an expression in here, and if the answer to that expression is this constant, then you'll execute this code. If it's equal to this constant, then you'll execute this code. Otherwise, you'll execute this code. By putting the break here, then if this constant is true, based on this expression, then it'll do this action and then just exit out. If you don't, then it will just do the next line of code. So make sure you put the breaks at the end for each of your cases for your switch. While loop, simply you test, and if the test is true, do the loop. For, again, you give it some initial value. You find out when you end. Reinitialize for each time through the loop. Very often this will just be a simple increment. Everybody remember all those, right? You should understand this table pretty good. At the very least, you should be able to spit out by memory, and I can almost assure you this will show up on a quiz. You should know from memory that hex 30 is the character 0. That hex 41 is the ASCII representation of the capital A. And that hex 61 is the ASCII representation of the lowercase a. And the unfortunate thing is the entire side over here has disappeared. Oh, the other one that you should pretty much memorize is that 20 is your space, just a blank space. So at the very least, memorize 4 of these. Otherwise, you could pretty much be expected to look up on a table, but you should know off the top of your head 20 is space, 30 is 0, 41 is A, 61 is A. So if you know what the digit 0 is, without having to look at this, the table, what is the representation of the character 9? 39. And you know that because 30 is the digit 0. You just add on and figure out what that is. What about uppercase J? Well, that's when you start to need your fingers, right? And maybe a little piece of paper. But you should be able to know A, B, C, D, E, F, G. Yeah. So the answer was
4A.
4A. Right? I said J, right? Okay. So, these are the types of things that, even though you could go through a book and look it up, you save yourself a heck of a lot of time if you just know that off the top of your head. Just like, what is the binary representation of the hex digit A? 1010. That's one of the easiest things you could do, because after that, if you're looking, what is hex C? Well, you know what A is, so just add 2 onto that and you can pretty much figure out, oh yeah, that's going to be 1100. So there are little things like that you should know. Just like, what is 1K? What is the value of 1K in decimal? Speak up. 1,024 decimal. So 1K, that's in the computer world K, not in the kilo world of liters and grams and stuff like that, right? 1,024, which by the way is what in binary? That's all I hear.
9 zeros.
Pardon me?
190.
1 and followed by 9 zeros, which means that 1K is equal to what value? 2 to the 10. So let me just. I'm going to do this. Things you should know. So this will be. You never know when something like this will show up on a quiz. Things that make you go, By the way, that's a song, right? An old song, right? Yeah, I'm going to have to Google this for you guys so you can, things that make you go, all right. What is your name? What is your quest? What is your favorite color? All right, ASCII 0, actually it should be one single quote, is equal to hex 30. ASCII capital A is equal to 41. ASCII lowercase a is equal to 61. And ASCII space is equal to 20. 1K in our world is equal to what in decimal? 1024, which is equal to what in 2 to the whatever? 2 to the 10, all right? 1 meg is equal to 2 to the 20th. So it is, and I like this. It's 1024 times 1024. Yeah, all right. Good answer. 1,048,576.
You're not gonna have me memorize that, are you?
Am I going to have you memorize that?
No.
No. By the way, something that's also very valuable is 2 to the 16th.
We can't see it.
Oh, yeah, we know. 2 to the 16th is 64K, which is 60.
5, 3, 5, 5, 6.
Where I gotta go back here again. $65,536 shows you how much I've memorized on that, right? And what was the other thing I said you should memorize?
That was it.
I thought there was something else. Yeah, I won't go and tell you the funny story I told in my earlier class. It's only for the special people from this morning. So here's a topic: masking. Masking is very common in embedded system. In other words, sometimes you want to isolate a single bit or a group of bits. So in this case, we can AND together these two numbers, and we can actually identify, see this bit right here, this 1 right there? We want to isolate that number or that position in this entire number. Or maybe I want to isolate bits 7 through 2. And so I would AND it with 1, 1, 1, 1, 1, 1, 0, 0. And then I would get all this stuff up here would be set to 0, because I'm ANDing it with 0. The stuff at the end would be set to 0, because I'm ANDing it with 0. And then what would be left is whatever bits 7 through 2 are up in this. And this is known as bit twiddling, and we often do that. By the way, a bitwise AND is the ampersand. A bitwise OR is the single up and down bar. If you use the double ampersand, that means logical AND. So let's look at an example. Ooh, something I added from earlier today, huh? So, assume you have, oh man, this looks so much better when it's, you can actually see it.
We can.
Oh, you guys can see it up there? Oh, what do you know? Let's see, if I want to do, oh, it's a Shift F5. Okay. Show it from the current one. Oh, I'm sorry. It's just on my screen that I can't see this.
Yeah, when you adjust the web browser, we have any web browser.
Say it again.
Like when you was on the internet and you just had to fit your screen,
Oh.
or get like smaller.
Oh. And nobody told me that. Okay, now you did. Sure. All right. So let's say you have the 3 switches up there. Notice I have switch 1, switch 2, switch 3, and it's connected to the 3 different ports. So if we have an integer is what? How many bits wide? Could be 16, could be 32. Depends on the compiler, right? Does it matter in this case? No, because I'm casting a single bit into an integer and then storing it into a variable. So in this case right here, here we go. This value will have, if I'm pressing switch 1, if I'm actually pressing switch 1, what will be the value inside data? 0. If nobody is pressing switch 1, what will be the value inside data? 1. Right? If I'm pressing switch 1, if I'm pressing switch 2, what will be, let me step back and say, think about this, we've got all three of them connected. Let's answer that again. So if I'm pressing nothing, what is going to be inside data? 7, right? Because in this case, I have, you know what, I can't point up there without my laser pointer. Where'd it go? Ooh, it's a laser. So, right now, if nobody's pressing anything, this value is going to be 1, this value is going to be 1, and this value is going to be 1, right? So that when I say, pull this in, that's going to be the value of 1. So if we look at this all at the same time, the data is going to be 7, right? Now, one of the other problems, and we'll see this later, is that, well, what about what value is in 1.3, 1.4, 1.5, 1.6, 1.7? They may be zeros. You never know. So in that case, I might need to mask it. So what would I do to mask it down here?
And 0, 0, 0, 0,
Right.
1, 1.
So maybe something to do would be to mask. I'm getting to it. I thought I would actually do a little bit of writing first, but apparently not. So in my example earlier, I had, let's see, data is going to be equal to, I believe I said port 1 dot bytes. By the way, I'm going to cast this into integer, and then I'm going to AND it with 7. I just do 7. That'll give me the 111 all the way at the end. So, data is equal to 7 if nothing pressed. This is from slide 17. So if we look at the other example here, now write the C code to interrogate the switches and print switch N pressed if that switch is being pressed, and print no switches pressed if none are being pressed. So, as an example, you're going to look at the bitwise AND for bit 0, then 1, then 2. So if the data is equal to 1, or I'm sorry, if data and you AND it with 1, and that turns out to be, let's see, 1 and 1 would be 1, which means it's not pressed, right? So if it is pressed, it'll be 0 at that position. We'll take the NOT of that. And so that means that switch 1 is pressed. So as an exercise, in fact, I'll let you go, but it might be something useful to do because you never know when it will show up on a quiz. Hint, hint, hint. What would be the remaining lines here and here for switch 2 and switch 3? And then, of course, if no press switches are pressed, what would that code be right there? Question. No, this is a homework problem in your mind that you never know when this will show up on a quiz. Is this on Moodle, the answer, or the slides? The slides will be on the web page by tomorrow, but they've also been emailed to everybody. Other than that, that is for today. Thank you.